A Hermitian operator is something, so we defined, if you have an operator, say O, we can define its matrix element in the following way. Somebody wants to come in. Okay, so if you have a matrix, if this is an operator, and then it has its matrix element, say OXX prime, is defined in the following way. If I take two wave functions and take the inner product like so, then of course the definition of the inner product is that we integrate over all space, and then the first factor is complex conjugated, and then we have some operator acting on the second factor. But what we can do is that we can then insert a Dirac delta function and then write the second half, this part, as, and we can change the argument to x prime. So, this will have some x argument as well. So, I should probably have, so this will become x prime, okay? And then what we do is that we say that, this guy, OXX prime, is defined to be delta x minus x prime O of x prime. Okay. Then we can write this inner product as psi O hat phi, and then some integral over dx prime psi of x, and now this is essentially a matrix element. OXX prime, sorry, this should be a star here, and phi of x prime. Okay. So this is how we define what OXX prime is. Now the index structure of this means that the second index acts on this wave function, and the first index, acts on this. And the analogy here is with matrix multiplication, right? If we have a matrix acting on some vector v, and then we take, so it will give me another vector w. Now, if I take another vector, say u, take its Hermitian conjugate, and then multiply this equation from the right, then we have essentially a number, right? And if I write this as in terms of its indices, what it is that it's aij, vj, u star of I. Okay? So once, so there are summation over I and j. But once I've written it like this, these are just numbers. We can just move them around. Okay? So similarly, this thing, the notation is telling us we can write this as say psi star of x, OXX prime, phi of x prime, and this is equal to say OXX prime, psi star of x, phi of x prime. So this, this and this has the same meaning, because because of the way that we have defined the indices, we can keep track on which index acts on which, okay? And then, we can also, write it as, say, psi star x, phi of x prime, or of xx prime, etc., okay? Now, it's not necessarily true that this has a value independent of these guys in this case, but, this is just notation. But it's kind of important notation, right? So then what we say is that, in analogy with, say, linear algebra, where we have Hermitian matrices, so we can define a Hermitian operator in the following way. First, we define what the Hermitian conjugation is. So this is the Hermitian conjugation. That means we have an operator O dagger. If I take its XX prime element, then that will be equal to the operator O, its X prime X element, and complex conjugated. Okay. So this is the definition of what it means to take the Hermitian conjugation. But being an Hermitian operator means that this operator will satisfy this relationship. Okay? This is what it means for it to be Hermitian. So if we imply this, then you can show starting from this expression. Where is this expression? Yeah, you can use this expression, or you can use the star of this expression to be precise. And let's just see how it plays out. So we start, say, phi, say, O hat psi star, right? What is this? This is dx prime phi of x O hat xx hat psi of this thing, complex conjugated, right? So then we can write this as dx, so there's a complex conjugation here as well. So dx prime, so this first factor just becomes phi of x, and this becomes star of xx prime, and then psi of x prime of star, okay? But we are saying that this is a Hermitian operator. It means that this satisfies this equation. So in the next line, what we can do is that we can say, well, let's just, get rid of the star, but the price that we pay is that we have to change the ordering of the indices. And then we can rewrite this as dx prime psi of x prime star O hat x prime x phi of x. But x and x prime are just dummy variables, right? So, I can just get the primes, get rid of the primes here and put primes here because they're just dummy variable. So that means that this is equal to psi O hat phi. So thus we see that, for a Hermitian operator, this means that it has to satisfy this relationship. And now if I take as an example for O, say the momentum operator, which is h by I del by del x, then you have to verify whether this operator satisfies this. Let me write the left hand side here, which is going to be phi or hat of psi. You have to verify that this guy satisfies this relationship. And if I want to do that, then the left hand side again is just del integration over x, phi of x, h bar by I, d by dx of psi. There's a star here, and the whole thing is inside is complex conjugated, right? So if I do this, then my first factor just becomes phi of x. This one becomes minus h by I, and this is del by del x psi star. Okay, and now what we can do is that we can do an integration by parts. Let's just, factor this guy out. If I do integration by parts, I get d by dx of phi of x psi star of x, and then there will be plus h by I d of x, and now this is going to act on this guy, so we can write a psi star of x d by dx of phi of x, right? And now, this is a total derivative, and so if I evaluate this, this is evaluating these functions at infinity. And if I assume that these functions go to 0 at infinity, as we should if they're going to be, say, L2 functions, then this factor goes away, and then this guy we can take inside, and therefore we have psi p hat phi, which is exactly what we had to prove. But of course, to prove this, we had to assume this, which is psi and phi go to 0 as x goes to infinity, right? And that's all we have to show. And then, the next one is show that p squared is, so when this happens, we say that p is self-adjoint. It's not just Hermitian, it's self-adjoint. So because this is an additional thing, additional thing that you have to assume, right? For this to be true, for this to be equal to this. Okay? So so in the infinite dimensional case, Hermitian is not enough. Our operators need to be self-adjoint. And then I leave the p squared, proving that p squared is also Hermitian. That's just a couple of lines of algebra as an exercise. Okay. But I just gave you an outline. You should try it yourself. Did you have any questions?
No, sir.
Is self-adjoint
Okay, so,
stronger than Hermitian?
Yes. Yes, it's because it's more restrictive, right? You cannot have any function, any old function. It's just when you study analysis, you might come across the fact that in analysis, an operator is only defined if you define the domain on which it acts. Where that's kind of implicitly clear when it comes in linear algebra, what domain it acts on. Even then, it's not, right? Because if I give you, suppose, I don't know, suppose I give you a matrix A, but I don't tell you whether it acts on Rn or Cn, right? Suppose it's an n by n matrix, right? For this matrix to make sense mathematically and physically, I have to tell you whether it's defined on Rn or Cn, right? So, but I think in analysis it's more subtle.